Welcome to the Object-Oriented OPC UA Client Tech Talk and Object-Oriented I/O demo. So this is me. I began my career many years ago with Chevron Corporate Engineering in San Francisco. I took a little detour from there into other areas of electronics and then back to my roots in industrial automation, where in 2010 I first encountered this CODESYS thing, and I was very impressed. It was far better than any other PLC system I had used and was right up there with the top high-tech electronic design tools I'd used earlier. I became more involved with CODESYS in the mid-decade, eventually helped start up the CODESYS North American office, and then took advantage of COVID to put all my knowledge of CODESYS into print. You can find out more about that at www.bookofcodesys.com. You can tap more of my knowledge on my YouTube channel at this URL, and I've contributed some interesting content to the OOIP Foundation at this URL. These videos and the postings on the Foundation mostly describe the subset of object-oriented programming I feel that the PLC community is ready to embrace. That subset that dramatically improves productivity while maintaining the high level of reliability, readability, and maintainability that PLC applications demand. The videos and postings also describe some libraries which help CODESYS make object-based programming possible. Two of these libraries are available on the CODESYS store: the Control Sphere Parameter and Persistence Library, which allows you to manage the parameters of your objects in a well-organized spreadsheet, and allows you to manage your persistent variables in a human-readable form which can be transferred to other systems. You'll see more of this in the Object-Oriented I/O demo. The Object-Oriented Alarming Library eliminates the need to create and maintain the lengthy alarm list. Just add your Object-Oriented Alarming enabled function blocks to your design, and their alarms just begin showing up in the alarm table. The Object-Oriented Logging is a new library that eliminates the need to build and maintain your trend list, and the Object-Oriented I/O allows objects to manage their own I/O, so the entire CODESYS device tree can be eliminated. We'll learn more about that at the end of this presentation. And finally, the reason we are here, Object-Oriented OPC UA Client. So let's jump into that one. In traditional PLC programming, we complete our code, then proceed with a number of post-processes necessary to complete the design, such as populating the alarm list, the I/O list, the log list, the persistence list, and so on and so forth. These lists take a great deal of effort and tend to be a significant source of errors, and need further effort to update any time the design is modified. It's common to create Excel or Python macros to automate some of this list creation process. You export the data from CODESYS, run the automation to extract the necessary data and format the results, then read the file back into CODESYS. But these homemade utilities are never documented, are usually lost or forgotten when the new hire is called on to update the software, or if your memory is as bad as mine, when you're called in 5 years later, or sometimes even 5 months later, and you've forgotten where the macros are and how to use them. Newer object-based programming allows you to develop a set of reusable objects that handle everything the object needs to do its job. You then instantiate those objects, and we're talking about function blocks here, in your design, and they just work. If you add more instances later, those new ones just work. No need to create or update any lists, create external tools, or anything. They just work, just like magic. Put them in a company library and everyone can use them, and they just work. The work you would have otherwise put into the custom macros is greatly reduced and is now built into your program, where it will never get lost or forgotten. You'll see me do tech talks on object-oriented alarms, object-oriented I/O, and object-oriented parameters and persistence. The latest to add to that list is object-oriented OPC UA. Not only does the OOOpcUA UA Client provide all the benefits of object-based programming, it, for the first time, provides for synchronous and event-driven programming with OPC UA variables. So what do we need to do to enable this magic? Let's get a quick overview before I give you a live demo. All you need to do is specify your tags, call a function in the library to configure your tags, and then add a method to move the read data to where you need it. Then you either tell the server to handle the reading and writing asynchronously, like is done with the CODESYS Data Source Manager, or you can trigger the reading and writing in your function block for synchronous operation. I'll explain all that more after the live demo. Then you declare instances of servers and instances of the OOOpcUA enabled function blocks, and you're done. Go online and the data will magically begin to transfer. So let's see what this looks like in practice. Here we have an example of a typical plant or factory design with a number of subsystems, all of which contain a number of motors. For simplification, every other control device has been removed, only leaving the motors sprinkled throughout the plant. So for instance, here we have the plant. It's got 3 assembly lines and some conveyors. We can look at one of the assembly lines, and it has a case assembly, case fabrication, a door fabrication, and a rack fabrication system. We can look at those fabrication systems. The rack has a wire feeder, a wire bender, and a wire robot. We can look at the feeder, and it's got a couple motors in it, a feeder motor and a cutter motor. Now, CODESYS has a great tool for object-oriented OPC UA server, and it's had it for many years. It's called the symbol config. Now, for some odd reason, they've recently announced the tool will be discontinued without any suitable replacement, but hopefully they'll come to their senses before it's too late. Anyway, using this tool, all you need to do is add an attribute above every variable that you want exposed to the OPC UA server, and then every instance of in this case, every instance of this motor function block, these variables are automatically exposed. Nothing else you have to do, no list you have to create or anything else. Just instantiate the objects and the variables are exposed. Couldn't really be any simpler than that. So we're just going to go online with this and get it off and running so we can use it in the next stage. All right, so let's look at the client side where the news is not quite as good. CODESYS has a tool called the Data Source Manager for accessing OPC UA variables on the client side. Now this is a traditional list-based tool for traditional PLC programming. So when you're done with your programming, you need to go back and populate this list, or anytime you modify your program, you got to go back and remember to modify this list. So we need to add one of those, Data Source Manager. Then we need to add a data source, and we're going to call it the Plant Control Server. So it matches the name of the server where we're getting the data from, and this is going to be an OPC UA server. We got to give it our the IP address of that server, and then it goes out and does a OPC browse on that to get all the objects from there. And we're not going to use the wizard. We're going to do our own mapping here. So the first step we have to do is create a type mapping. So we got to map the motor that's on the server to our motor that's over here. And we got a little motor. It's very simple. It's just got one variable. That's all we're going to use right now. I'll show you a much more complicated example shortly. Anyway, so we need to go get a motor. Now you'd expect that to be able to find a motor in here because that's what it's called on the server side, but that's not how this works. Somehow you've got to pick an instance of a motor to get the motor type. So I think that's a little bug, but whatever, it seems to work. And then we got to give it some arbitrary mapping name. We could call it anything we want, but I'm just going to call it motor because that makes a lot more sense. And then we need to we're going to map it to a local type, and we want this to be this motor client here. So we've mapped the type. Now within that type, we've got to map the variables. So I know I want the RPM, so I can just type it in here, or we can use a wizard to go find it. Okay, that doesn't work. Okay, guess we do have to do just RPM. Okay, and it already knew it was a real number, so it filled that in for us. And the local variable is not RPM because remember, over our motor we called it RPM OPCI. We have that naming convention that indicates that it's a OPC UA input. Okay, so we got that step done. All right, now we got to do the mapping. Well, first we got to have something to map to. So we have to create an instance of this. We'll just call it M1, and we're going to call it motor client. Okay, and then we have to map to that. So first of all, we have to tell it what we're going to map there. And this is where we go get that one of these motors. This diverter motor will be fine. And we're going to give it the type mapping that we declared earlier, that motor. And then we got to give it a local variable. So it's going to be plant.m1, right? And we always update, and it's mapped. Okay. So that's what we need to do. And then if we had, any additional motors, we'd have to add additional lines to this list. Or anytime we, modified our design, we'd have to come back and remember to modify this list accordingly. Also, this example assumed you had network access to the server while you were programming the client. If you don't have network access, the process is much more complicated. Now let's contrast that to the object-oriented technique. Just declare an instance of the object-enabled client from the library and tell it where you want to get the data from on the server. That's it. Notice we don't need network access to the client for this process. Then go online and see the data being transferred for both instances. Now let's take a look at the magic that goes into making a function block object-enabled with this very simple example. We do need to do a little bit of one-time work to our local motor, but let me emphasize, this is one time in the life of this motor. Stick this in a library and no one will ever need to duplicate this effort. For this, we will make a copy of the simple motor so we can add the necessary items to make it object-oriented. We'll call it motor client OOPcUA. First, we need to have this function block extend the equipment base class. That's just a function block I created that provides certain features like providing the instance name. And then we have to have it implement the OOPcUA callback interface. And I'll show you the significance of that shortly. Then we need to add 3 variables that the OOPcUA needs, such as the OPC node ID. This is the node ID of the variable as it's known on the other controller. An array to hold the variables we read from the server, read vars. We will only be reading one variable for this simple example, so the array only needs to be one big. And then we need our first scan flag. We then need to add our first scan logic to configure our read variables. We call the configure read var function in the OOPcUA library and pass it the array we declared above and the node ID we want from the server. Then we need to trigger the read. We do this by calling the read vars method on the server we declared earlier and passing it the array we configured earlier. We also pass it the this pointer, which is a pointer to this instance, and I'll show you the purpose of this shortly. Then finally, we need to implement the interface which automatically adds the necessary methods to our function block. Then we need to add code to the read callback method. When this client reads the OPC variables, it will use the this pointer that we mentioned earlier to call this readback method, passing it an array of the values that were read. We need to move the value from that array into our function block. We do that by making an assignment to our local variable. Remember, it's called RPM-OPCI, and it's going to get passed to us in the 0 member of the P arrays because there's only one value being passed, and it's extracted as a float, which is OPC language for real. And that's it for this one-time process in the life of this motor. Next, we need to specify a server. This is a one-time effort per design. We do that by declaring an instance of the OOPcUA server and specifying its IP address. If security were enabled, we would need to add the security parameters as well. But for this demo, we're going to keep it simple. We can then instantiate a motor client, OOPC, that we just created. And then we need to call both. Now we can go online with our client and watch all this magic work. The data from the motor on the server is transferred to this object-oriented OPC UA client as expected. Now, this was an incredibly simple example, but I have a little more practical example here prepared for you. This one reads more data from the server, and it also writes data to the server. It also has a motor visualization block tied to its motor function block to make it a little more realistic scenario. First, the tags in the server are configurable instead of hard-coded like we had in the first example. So for each instance, we can specify different parameters. This also reads many more variables, and it also includes variables that it writes back to the server. The client reads the server's instance name so we can check that we are connected to the correct motor, and it writes its instance name so that there can be some cross-referencing on the server side. It also does a read-write on the heartbeat variable so we can be sure the data is fresh and so we can monitor the round-trip data transfer time. We have some first scan logic which configures the tags. I'll show you that in a minute. And some logic for the one-time read and write data so we don't need to be continuously transferring those instance names that never change. And then the line of code that actually triggers the read of the other variables on every scan. So let's look at the logic that configures the tags. In this demo, we're building up the tags using input parameters that we passed in. First, we have the boilerplate that is in every CODESYS server tag, dot, the application name, dot, the motor instance name, and then dot, and the specific variable name on that motor. Then we call the configure functions for each of these tags to fill in the read or write arrays. Then we have to do a little work for the write variables. For the one that continuously changes, we just provide a reference to the local variable. That one's easy. For the instance name that doesn't change, we just hard code the address of the local string variable, and we also need to give it the length of that string. That local string is automatically filled in with a path to its instance using that equipment base class that I mentioned earlier. Now, if we wanted, we could register our read-write variables with a server like this and let it do the work asynchronously on its own task, like how the Data Source Manager works. But in this case, we want to do the transfer synchronously, so we've put the code to trigger the read back in the body of the function block like I showed you earlier. Notice we provide the this pointer, which is a pointer to this instance of this function block. Remember, the OOOpcUA library uses that pointer to pass the read data to the read callback method. The write operation will be triggered in code that we will place inside the read callback method in order to perform a synchronous write. I'll show you that in a moment. So the way this works is this line tells the OPC UA server instance on our client side to request data from the server on the other controller. The return data from that controller triggers a hardware interrupt from the TCP/IP chip on this client. That interrupt service determines which instance of this function block issued the request and then uses that this pointer to pass the data to the read callback method on this instance. The read callback does what we talked about in the simple example, but this one is a little more complicated. First, it needs to determine which request the response is from, the read of the instance name or the response to the read for the dynamic data. Based on that, it moves the data from the p-values array we talked about earlier into the variables in this function block instance. If the response is from the dynamic data, we then have the method perform some event-driven functionality and perform a synchronous write. In this case, the functionality is to update the heartbeat and calculate the round trip time. Then we send the updated heartbeat back to the other controller with this write command. So notice we received the update data, performed some functionality, and then wrote the resulting data back. This is actually quite revolutionary behavior for OPC, which I'll cover in more detail in a few minutes. Then we have 4 instances of this motor declared in the program. Notice in the declaration we specify the server, the application name, and the path to the motor on the server for each motor. Then we call each motor. That's all we need to do. Bring in the instance from a library if you want it accessible to your entire company. Tell it which server has the data, the application within that server, and the path name to the specific instance on that server. Once you have it all set up, it's just that easy. No need to go back and update an OPC UA list or anything like that. Just put it in and it works. So we go online and look at the visualization, which shows us the status of our 4 motors here in the top half. At the top of each, we have the instance name that was transferred from the server, so we know we made the correct connections. We have all the data from the instance, and at the bottom, we have the round trip time calculated from the heartbeat variable we saw earlier. Now, how easy is that? Now, hopefully your motors aren't quite as active as these, but you get the idea. And I'll show you these visualizations in the bottom half in a minute. So, just to emphasize how easy it is, let's go back and add another instance to the server. Remember, the symbol config is already set up for object-based programming. We just need to add an instance and it does everything necessary. No listing, maintain, or other complexity. Let's call this one Gary. Then we'll do an online change to make that active. Then we go to our client, add another instance. Let's call this one Pratt, and we give it the path name to Gary on the server, and then we add a visualization to go with that new instance. Then we go online, and voila, they're just communicating. It's just that easy. No communications managers list to create and maintain on the server, no tag lists to generate, no data source manager list and mapping to maintain on the client. Just place the objects, and they work. It's just that simple. For those of you who have taken my class or read my book, you will have seen the feature CODESYS provides that allows thousands of tags to automatically be connected between a visualization and a control when the two have matching structures. Now the same can be done with OPC UA. Here in the client, I have a plant structure that is identical to the plant structure on the server. But now, instead of using parameterized motor viz like we did in the previous example, we use a motor that generates its node IDs automatically based on its instance's path name. So the motor needs no parameters when they are declared. So we can go online with this and drill anywhere into the plant structure and see that the 140 motors on the client side are automatically connected with the matching 140 motors on the server side. All automagic. I've placed 5 of these in the visualization to show the connection, but taking this one step further, had the visualization had the same structure as a plant, we could have had 140 motor visualizations connected to their corresponding function blocks automatically as well. This doesn't need to be restricted to matching plant structures. Tags on the client side could be automatically matched up with any regular pattern of objects on the server side. It's really only limited by the imagination. Keep in mind that to do this with the traditional post-process list-based PLC programming paradigm, we would need to manually enter 140 lines into the Data Source Manager list and maintain that list. With object-based paradigm, each object includes the intelligence it needs to do its job. As I mentioned earlier, the object-oriented OPC UA client gives us many different options. First, we can make it operate asynchronously, like the Data Source Manager does, or synchronously, like the demo you just saw. Then we can make our functionality scanned, like traditional OPC or remote I/O, or event-driven, like you saw in the demo, where the receipt of the input data immediately triggers our functionality, like the PLC programming is done with local I/O forever. Then we can hard code our parameters like we did in the first example, or parameterize everything like we did in the second. Hard coding your tags is a good option if you're connecting to something like a skid where the tags for each skid are identical and the only difference is the server IP address. Let's reiterate this new ability to perform synchronous event-driven programming with OPC UA variables. Here's a process cycle for every PLC you have ever programmed. You read your inputs, execute your program to generate outputs based on those inputs, write your outputs, and wait for the remainder of the cycle. This is synchronous programming. Reading and writing your inputs and outputs is synchronized with your program, and your program reacts to changes or events in those inputs to generate your outputs. Now you can do the same thing with remote OPC variables. As this snippet of code shows, the OPC client library calls you and says, hey, I've got your OPC read data. Then you check to make sure it's valid, extract the data, execute your program on that data, and then write your outputs back to your OPC. All right here. There's actually nothing in the body of this function block except just to trigger the next read. This works especially well with read-write variables for handshaking. In traditional OPC, you have no idea when the data is actually being read or written. This can be a big problem with asynchronous tools like the Data Source Manager, because you never know exactly when your write data is going to be written. You have two different processes running at their own rate. The OPC cycle is completely random to your program cycle. You could write your handshaking out too late to make the OPC write cycle. Then your OPC read cycle comes back in and overwrites your handshake. So let's go through that one step at a time and make it a little more understandable. The server sends you a true to trigger you to perform some functionality. You perform that functionality and then you write a false to confirm it was completed. But your program writes that false too late and misses the OPC write cycle. The OPC next read cycle comes in and changes your false back to a true. The server never receives your handshaking confirmation and doesn't know it is clear to trigger another. So the system locks up, and it does so randomly. Sometimes your program writes the data in time to get it in the current OPC write cycle, and sometimes it doesn't. It appears to be a random bug. Very frustrating. Fortunately, with OOOpcUA, you can now incorporate the OPC process cycle directly in your PLC process cycle and never worry about this asynchronous problem again. This slide shows the interaction between your program code, the OOOpcUA server in the OOOpcUA library, and the CODESYS client library. I'm not going to go through this, but it is here when the video is posted, so if you want to get more detail. And it'll be in the next edition of the book of CODESYS. Okay, so that is Object-Oriented OPC UA Client. It complements the Object-Oriented OPC UA server that has been available from CODESYS for many years. Just add a little code to make your function block self-contained and self-reliant, and then you're done. Drop these enabled function blocks in your code, configure them, and away you go. And add more to your design later on, and they just start working. No list to go back and remember to modify, no one-off custom Excel or Python macros to build or maintain, just plug and play. The ultimate easy button. Anybody remember the easy button advertising campaign from the 1990s? So this demo is posted on the OOIP-foundation.org website, and the prototype source code for the underlying library can be purchased from ControlSphere. Just email me for more information. So that concludes the portion of this tech talk on the Object-Oriented OPC UA. I hope you have lots of good questions for me in the Q&A session.